Vale, estamos ya y son 5, así que adelante, Marc.
Molt bé, doncs, benvinguts a tots. Aprofitant que fa poques setmanes va ser el Clean Energy Day, la Sabela va proposar de fer dintre l'eix d'energia i mobilitat unes presentacions, doncs això, ressaltant els projectes que estan relacionats amb l'energia neta. I al final ho hem dividit en dos workshops, un és el que fem avui i l'altre és el que fem la setmana que ve. El d'avui tracta sobre energies sub-watt, microenergia, i presentarem 3 projectes que estan relacionats amb el tema. La Llibertat parlarà del projecte nanoDecoTEG, i jo mateix parlaré després del projecte ThinTEG, i en Carlos Carbonell presentarà un projecte anomenat Creedence Clearwater Revival. I tot això és dintre del grup Messi, que estem a l'IMB-CNM, així que dono pas ja a la Llibertat, que anirem una mica justos de temps, amb els 10 minuts per presentació. Així que endavant, Llibertat.
Molt bé, doncs moltes gràcies. Marc, sisplau, descomparteix, perquè si no, no em deixa compartir.
És la Liber, jo no. La Sabela.
Vale, ja està. Estic compartint, que sí?
Sí, es veu.
Es veu en gran ja?
Encara no.
Sí?
Ara sí.
Ara sí? Estupendo. Doncs comencem, si voleu. Hello. Thanks for the introduction. First of all, I would like to thank Sabela and the coordinators of the Energy Axis for giving me the opportunity to present this project from the MESI Termitas group. This project is coordinated between 2 partners, UAB Physics Department and Instituto de Microelectronics of Barcelona. Before explaining the project, I would like to give a brief introduction on why we propose it. Energy efficiency is a major issue along with global warming and the need for sustainable energy. These flow diagrams show Spanish primary energy sources, and energy losses appear in the upper and right part of this graph, while useful energy is in this lower part, right. For example, in automotive sector, only 25% of the energy is used, with the rest lost as the heat. Key cause of low efficiencies is thermal loss during energy conversion and distribution. On a micro scale, thermal loss is also important, as you know. This infrared image shows a microprocessor with temperature difference of up to 30 degrees. The Internet of Things is boosting, in other part, MEMS technology, making sensors, processors, batteries, and transmitters smaller, more efficient, and affordable for widespread industrial use. Wireless networks are now nearly everywhere. It is clear then that not only will be abundant energy we needed to power the entire sensor network, but it must also be distributed or ideally generated on site to minimize losses during transmission and distribution. In this context, we believe that thermoelectricity could be a potential approach to mitigate the oncoming challenge, serving as a clean and renewable energy source. The key variable in thermoelectricity is this figure of merit, which depends linearly of the Seebeck coefficient and electrical conductivity, will be inversely proportional to thermal conductivity, the electrical one and the phononic one. When comparing the efficiency of thermoelectric materials to that current thermal machines like Stirling or Rankine engines, thermoelectric materials still far short of their performance. One milestone in thermoelectricity was presented in 1993 by Professor Mildred Dresselhaus. This theoretical study predicts that reducing dimensionality would increase this figure of merit by lowering principally K. Before this prediction, thermoelectric materials were bulk-based, mainly used in chalcogenides in general, in bulk chalcogenides, with figure of merit around 0.5. After Dresselhaus theoretical work, nanostructured bismuth material thin films, and even silicon-based nanotubes, nanowires were developed, achieving figure of merit around 2. At this point, I think that it's very significant to mention that these nanostructured materials are difficult to integrate into CMOS technology and also are naturally scarce. One of the most abundant materials in the earth, as you know, is the silicon, which also has a mature technology that could enable large-scale production. Unfortunately, bulk silicon has very low TC in comparison with other inorganic materials historically used in thermoelectricity. In this, in particular, it's almost 1-2 orders of magnitude smaller than other materials. But in the same volume of Nature, 2 articles were published that mark another milestone in thermoelectricity. They show how silicon nanowires can achieve up to a 100-fold improvement in this figure of merit. The project that I present here to you takes advantage of this great opportunity. It's based on the idea that functional thermoelectric materials can be created from nanostructured or decorated thin films. These materials will have optimized thermal and electrical properties and could be integrated into microfabricated thermoelectric generator. The goal of this project is to use this microgenerator to power Internet of Things nodes, replacing the need for primary batteries. I want to go into detail, but it's clear that the use of nanowires is not ideal for the implementation in devices. Some of the reasons are the integration of a large scale is difficult and the controlled growth is very complicated. In the nanoDecoTEG project, 2 strategies based on the thermoelectric thin films are proposed. The first one will be decorate thin films of silicon with metal nanoparticles evaporated to reduce thermal conductivity K, and therefore improve the efficiency of the generators. This strategy will be part of the master thesis of Marc and Hugo PhD thesis. On the other hand, we will use maglev block copolymer lithography in thin silicon films with the same goal as this previous strategy. This work will be reflected in Alex's PhD thesis. But our objective in this project is clear. It's to implement these thin nanostructured layers in microtegs, such as traditionally we develop in our group. Here, I show you some examples of these platforms. Unfortunately, I cannot show you at this moment measurements of the microtegs with nanostructured silicon films, but I can show you the first generator with nanostructured thin films by BCP, by block copolymer, that Alex is trying to measure in these weeks. And to conclude my presentation, I would like to show you some results regarding the reduction of thermal conductivity that we are achieving through dimensionality reduction, and in particular with decoration. We are still in the process of cleaning and connecting these chips, but we are confident that the measurements will provide you the information for the thermal conductivity as a function of silicon thickness with and without decoration, and with resolution that represents the current state of the art in this technique. And thank you for your attention.
Okay, thank you, Llibertat. Next one, we go to my presentation. Actually, let me try to share screen. Okay, you can see the screen, right?
Yes.
Okay, So I'm going to talk about this project, which is called ThinTEG. The title is silicon-based microthermoelectric generators with thin film silicides and perovskites, and it's mostly the participants in this project are listed here. Most of the people are group MESI. In thermoelectrics, I'd like to start with this infography from Libelium, which is a Spanish company dedicated to Internet of Things, which highlights the effect or the transversality of the Internet of Things sensors, which are distributed sensors, which can help provide information of industrial processes or wildfire prevention or crops optimization, and all these processes need sensors, and these sensors are usually these IoT nodes. Okay, an IoT node typically has sensors and actuators, and it can have also, it needs to have a power source and some wireless communication capabilities. The energy part is what we are trying to solve in this project, how to power these devices, because most of them don't have access to an energy network, so they cannot be plugged into the power source. They use primary batteries instead, which is the fast solution or the commercial solution to these problems. The problem of primary batteries, when you have a lot of sensors, like millions of sensors connected, is that you have an environmental problem to replace, not only for the environment, but also the logistics problem to replace the batteries once they are exhausted. So the natural solution is using energy harvesting. Typically, in the small and the low range of energy sub-batch application, the possibilities are solar cells, thermoelectric with temperature gradients, mechanical excitations, which use piezoelectric harvesting technologies, or triboelectric, or RF energy collector. Another problem we have with IoT nodes and energy harvesting applications is that not always the energy is available when the IoT node needs it. So there's an intermittent energy source or sink. Therefore, we use secondary batteries to apply that. So energy harvesting is used to charge these secondary batteries. And in the between is usually, it's used these power adapter options, which are called MPPTs, stands for maximum power point tracking. And there are a lot of commercial companies working on that, and they have efficiencies of above 90%. So they are already optimized part of the project, and they are able to extract the maximum energy from the energy harvesting sources. I would also like to highlight the Sustainable Development Goals from the United Nations. Again, we are talking today about number 7, affordable and clean energy, but I would like to highlight the application of this energy harvesting applications and the IoT. It's transversal, which is also, therefore it also has applications in industry and infrastructure monitoring, sustainable cities, responsible consumption and production, as well as climate action. So the project is ThinTEG. It is a coordinated project in the national plan, and the coordinated project is called PowerDot, actually, which is thin film-based microenergy harvesting and storage devices. So we're trying to put together a harvester, and you see my pointer? I assume
Yes.
Okay.
Yes.
So we have a thermoelectric harvester and a proton battery. Okay, both of them are new developments because they are using thin film and non-conventional materials. The proton battery is a thin film battery which has been developed at IREC with Alex Morata and Federico Baiuti. It's called Llibertat because it's using hydrogen instead of lithium, which should be the conventional commercial applications in conventional batteries right now. And in the ThinTEG, we are using microthermoelectric generators, but in thin films, but with silicides and perovskites, which is also a novel development. Not because of the material, but yes, because of integrating that in thin film form on thermoelectric generators. So there is a structural distribution of the board packages. We have been collaborating with IREC for, 15 years, more or less, because we are quite complementary. We are experts in microfabrication, and they are experts in materials, so we try to collaborate a lot in applying these two expertises in developing devices. And as you see, we are developing silicon micromachine architectures to deposit the materials that they develop. And this is what we are using in both applications, in the battery as well as in the thermoelectric generator. silicides. What are they? Liber already mentioned this ZT figure of merit, which is Seebeck coefficient of the material, the electrical conductivity, and the thermal conductivity on the bottom. We're working on mainly 3 different silicides. Silicides are just silicon with alloys with silicon and different materials. Typically in the literature, when you use for they are used for thermoelectrics, they are using magnesium silicide or chromium silicide, which are the, let's say, the in between of the most performing and something that it's CMOS integratable or compatible with what we are doing at the clean room. The magnesium part, at least, it's not being carried by us, because magnesium actually turns out to be a very harmful, complicated material to manipulate in the clean room. So it's actually developed by IREC on substrates that we prepare, and then they come back to us in a form of the silicide of magnesium, and chromium silicide is being developed here by us through different RTA processes I will mention later. And we're also ready to integrate also silicon germanium, because we have targets already available, and we are waiting to try to co-spatter them on thin films, in thin film form on substrates that we have been developing. The silicides have already good Seebeck coefficients and good electrical conductivity, but we're trying to reduce the thermal conductivity by nanostructuring them. Okay, this is the state of the art, more or less, over what has been done in silicides. And you can see here on the top the chromium silicide, and here the magnesium silicide. And you can see that they have already enough competitive, let's say, or state-of-the-art electrical conductivities, and they have low enough thermal conductivities. We want to reduce them further by using tens of nanometer thick layers to improve or to reduce the thermal conductivity, and therefore increase the ZT factor. These are reported at ambient temperature, if I recall right, but if you increase temperature, this figure of merit are even better than these ones. And the second type of materials are perovskites. Perovskites are ceramic materials which have the form of A, B plus oxygen 3. And the ones mainly used in thermoelectrics are titanates of strontium or manganites or cobaltites. Okay, these are the conventional ones. We're trying to improve them. Improve them in the sense that perovskites, for example, have a good Seebeck, have a low enough thermal conductivity, but they don't have a proper electrical conductivity. We try to improve that through that there is a work being developed at IREC as well, through doping and different type of materials. What we are trying to improve as well is exploring these high entropy oxides to reduce further the thermal conductivity. What they are perovskite extractors, but in the A site we use not 1 but 4 different anions, and the same thing on the B side. And these are the main extractors that are being tested right now at IREC to fabricate them, optimize them, and then try to deposit them on our substrate. They use that for that. They use a PLD machine. And they already have been having successful devices, successful materials. But now we are in the middle of the project, and now we are starting to grow them on our substrate. And I guess, as I mentioned, this project is the first attempt to integrate these complex materials as thin films onto these silicon-based substrates for thermoelectric generation. The objective is to obtain open circuit voltages of 0.6 volts, power densities larger than 100 microwatts per centimeter square, and ZT factors or ZT figures of merit in this temperature range around 0.15 or 0.3, which would be already competitive and beyond state of the art. The silicon platform that we are using for this, I want to highlight the work developed by together with Joaquin and Inigo, who was collaborating with us at that moment. And it was developed in a harvester project, again, an European project that we were working with IREC at that moment. And I would like to highlight that we prepare substrates by making a pre-membrane, not a full membrane, and not releasing the membrane completely. And then is when we deposit the material by PLD. In this case was a work developed at Harvester with DTU, a group of Nini Brits from Denmark Technological University. And then when we receive it back, we develop and optimize the patterning at the dry etching by physical bombardment, and then reprocess by argon ions in order to etch them, because there is no chemistry available for etching this type of materials. And then we deposit the rest of the layers to make these functional membranes. Okay, this is the chip that we are developing so far, which is a 1.5 by 1.5 centimeter square, and in between we have 5 membranes which have an integrated heater for test purposes. We heat the central part of the membrane, and we externally, we produce this temperature gradient between the inner part and the external part of this membrane, which is the STO material. And then we can contact them with collectors, the internal collector and the external collector, and extract energy and evaluate Seebeck coefficient, electrical conductivity of these materials. And then in harvest mode, we don't use the heater. We just put them on a hot plate, and we try to cool the central part of the membrane with special adapters that we design and fabricate in silicon, which help us contact the central part of the membranes, which you can see there, and produce or maximize this temperature gradient. Actually, I would like to now show the chromium silicide fabrication that we have optimized already through different RTA processes. In this case, we start with a 50 nanometer silicon from an SOI wafer, where we grow 25 nanometers of chromium. And after different temperatures and times of RTA processes, we end up having 60 nanometers of chromium silicide. You can see this is the as-grown material, where you can see the peaks corresponding to chromium. And as you increase the temperature over time, they start disappearing, and we start seeing the peaks corresponding to chromium silicide. And this has been done for 25 nanometers of chrome as well as 50, and you can see in the 50 we are not able to get rid of the remaining of the chromium silicide. And now we are doing that not only for silicon, crystalline silicon, but also for polysilicon, to being able to grow it on the device I was showing before. I would like to finish with the previous experience we had with this niobium dope STO, that we already have measurements of this platform integrated on a PCB and with a heat exchanger on top, and we can see that the performance is increased a factor of 10 at least, comparing the natural convection case, which is this case, to the forced convection plus the dissipator on top, where we can see that the performance is much more increased. Again, this is not the optimum geometry or architecture. This is just to test the device. You can see that the power output is quite low. It's around 8 nanowatts. But we're trying then, once we have these values and once we know the performance of the material that we are able to grow on these platforms, then we will need to optimize them and trying to increase the power density and structure similar to what we did in the silicon nanowire case, where we were integrating a lot of these geometries and optimizing the geometry to maximize the power output of this material. And I would like to just thank the fundings for this material, as well as the Clearwater ICTS available. So that's all from my part. I will stop sharing, and next talk will be given by Carlos Carbonell.
Okay, let's see if I can share this. Pantalla 1. Compartir. Okay.
Yeah, we see it.
Are you seeing the main one, or are you seeing the second? Yeah.
No, it's the second one.
So I have to change, right?
If you go to display settings on the top, I think you can switch them.
Let me see. Display settings, swap. Okay.
No, it's going. It's okay.
All right. So, well, thank you, Marc, and Liber and Sabela. The project I'm talking about today is it's about trying to obtain electricity from moisture. Moisture that can be in the air, or can be from a body, from human body, or can be on like in here is represented from a clay vessel or a botijo. This is a collaboration between the Thermoelectric group and the supramolecular nanochemistry and materials group at the ICN2. And I'm just gonna briefly introduce the topic. Well, we all know for millennia how to obtain energy from moisture through, for example, sorption, or the most the technology that we probably know the most is the desorption cooling, which is the mechanism behind the cooling effect on the clay vessels. But probably this technology, the electricity generation from moisture, it's something that we are not very familiar with because it's pretty new. So there are different mechanisms that could explain how to obtain electricity, but I'm going to focus on one, which is the diffusion based. And in here, we see that what we are going to need is a hygroscopic material rich in oxygen functional groups or nitrogen functional groups, which contain protons, which upon water absorption can be ionized and then will diffuse. And the idea is to use this kind of electricity to powering wearable devices, IoT, etc. This is very briefly the mechanism of this technology. In here, we have the material with the protons, which are bound to the backbone of the polymer or the graphene that contains the oxygen. When this material absorbs water, the protons dissociate, and then we have two different effects here for the ion flux, right? We have diffusion from the higher concentration to lower concentration, and we have migration, which compensate a little bit the diffusion, although this one is more significant. If we can maintain a gradient of humidity in the material, for example, by blocking one side of it, then we will reach a steady state. And I cannot go into much detail in 10 minutes to explain this, but well, basically we will generate an electric potential which we can subtract. This is an open circuit. If we close the circuit, what happens in here, it's complicated. There are a lot of things, and it's still not very well understood. So this is an opportunity also. And this was first discovered very recently in 2015, this paper in Advanced Materials, where they use graphene oxide and they selectively oxidize, creating a gradient of oxidation. And then they just demonstrated by absorbing water in one side, they could generate some electricity. Since then, there are about 1,200 papers that has been published using this technology. It's a little difficult to keep track of all the novelties. Sometimes I don't even understand why people keep publishing, because performance of new papers doesn't seem to improve what has been published last year. But there are a lot of factors here, like scalability, like green technologies to fabricate, and well, here I just wanted to show you very briefly two examples of papers published last year, which are among the best performers, and just to have an idea what the state of the earth in terms of performance are, which is like around 1 milliamp per square centimeter and 1 volt generation. And if you see the architecture, this is a pretty simple architecture. This is one material, an alginate cross-linked with calcium ions and also infused with sodium chloride. This gradient is capable of generating 1.2 volts and 600 micrograms per square centimeter. The electrodes, where there is like a wide variety of materials and architecture that has been explored. But what it seems to work pretty well is an interlayer of PSS and then a metal electrodes. Some interesting fact is that they all require high relative humidities to operate at the best performance. And here is where I saw the opportunity. Well, this is a different example where you see that they are implementing a new layer, which is an evaporative, and there is also some sunlight heating, some radiative cooling. And the materials, again, are just a polymer, PVA, with rich in oxygen groups, and also doped with another molecule which has a high density of phosphonic acid groups. And again, we see that the performance improves drastically with high relative humidities, and that's something which is common to all the systems. So what challenges and opportunities we have in this kind of technology? This was published in Nature Review Materials, and in here I just want you to see how this looks. This is like a device, macropore, mesomicropore, and molecular scales. And if you see, the problem or the challenge comes from disordered structures. because if you see here, the opportunities, everything is like better order, and that facilitates heat and mass transport. And so when I saw this, I thought, well, here we might have an opportunity, because my expertise is one kind of materials, which are precisely reticular materials. And let me briefly introduce you why those could play an interesting role in this kind of technology. So for those who doesn't know, very briefly, metal organic frameworks are these coordinated or coordination polymers composed by a metal linker, which is coordinated with a ligand, and they form a crystalline structure, a powder material, which is modular, meaning that you can basically choose the metal you want, you can choose the ligand you want, you can functionalize inside the pores with the functionality that you want. And this, of course, gives like a lot of applicability in any field that you can imagine. The most important characteristic is this one, right? One spoonful of this material have the equivalent specific surface of a soccer field, 7,000 square meters. And you can apply them, well, they've been applied in every imaginable application possible. But the one application that I thought about is this one, which is water harvesting. This graph is the different materials, represent the different materials that how much water can they absorb at different relative humidities. No, we have that hydrogels are the ones, the materials that can absorb up to 7 times their weight in water, but they require high relative humidity. However, we have materials like zeolites, which they absorb water at almost no relative humidity. As soon as there's some water in the environment, it goes to the zeolite. But desorbing from the zeolites is pretty energy requirement. It requires a lot of energy. However, we have this blue area here, which are the metal organic frameworks, or this one also, which are the covalent organic frameworks. These materials have the whole range of humidities, and they require less energy in order to desorb. Those are the typical water absorption isotherms of metal organic frameworks. You see some, they begin absorbing, but at certain relative humidity, they have a sharp increase and to saturation. So this means that they saturate at low relative humidities compared with the hydrogels which have this shape. They keep absorbing, but they do not, they have a high capacity, but they require high relative humidities. So my idea was to combine both, right? Combine metal organic frameworks and hydrogels or polymers to see if there is some transfer of the water absorbed in here to these kind of materials. And that would be only for one part of the moisture electricity generator architecture, which is the water harvesting part. If we can have a layer for the water harvesting, which would be polymer gels, polysaccharides, or composites with the metal organic frameworks, but also for the active layer, and I will show you in the next slide why that metal organic frameworks could also play a relevant role. The rest of the architecture or the elements are more well known, and it doesn't require that much exploration. But this is basically what the project consists of. At the ICN2, they have synthesized this MIL-121 aluminum, which has this crystalline structure. And I cannot think of another material which has a higher density of ordered free protons inside the pores, as you see here. This is let me see if I can rotate this for you. You have these windows, right? So water can go inside here, and inside the pores, it has free ligands, which are tetracarboxylates. And in addition, sorry, I was pointing here. Inside the pores, it has 4 free ligands. So it has 4 free carboxylates, and in addition, the ligands forming the structure also have 2 free carboxylates. So this density of carboxylate groups seems to be ideal for this kind of application. But of course, this is a powder material, and you need to structure. So you need to combine with the typical materials that have been used for moisture electricity generators, which are PVA, or polystyrene sulfonic acid, which is what we are doing right now. We're exploring these materials. We also added some polyethylene glycol diacrylate, and what we see in this slide is that the hypothesis is confirmed. The more metal organic framework loading we add into this system, the higher the open circuit voltage we can generate. Here we can obtain 650 millivolts. Unfortunately, the current is very, very low compared with the state-of-the-art literature. That can be for different reasons. So we are exploring what that can be due to and how to improve that. One reason is the electrode. The electrode plays a very important role. So here, for example, we just changed the electrodes, and we could obtain with a silver and steel electrodes, we could increase 25-fold the current, but the voltage decreases twofold. And the second hypothesis is because of the material that we are using, the polyethylene glycol diacrylate. This is not electroactive. So we tried with just pure polystyrene sulfonic acid, and here we obtain an increase of 1,000-fold, the orders of magnitude. Here we are in the microamps already. And the open circuit voltage also increased a little bit, not as much, but a little bit. We have room for a playing here, and this is a very early stage of this project. We have many directions we need to explore: the architecture from the molecular to the device scale, the active layer, which is the MOF influence on ISC and VOC for the better polymer systems and electroactive polymer systems. And then for we need to study what the potential synergies of the MOF hydrogel, and then the electrodes, and ideally the applications, if we could fabricate self-power wearable devices in the collaboration with the group of Aplicaciones Biomédicas. So this is pretty much where we are. Here I just wanted to show you a couple of SEM pictures of different architectures of electrospan MOF PVA for water harvesting, with a lot of surface and the MOF inside the PVA fibers. And this is an aerogel of the MOF PVA PSSA for the electroactive layer or the active layer with this hierarchical porous structure. And well, with this is pretty much it. Thank you very much to all the Messi group, and also to Inigo and Francesc, to Gemma and Tom from GAP, and from the ICN too. Thank you.
Molt bé, merci, Carlos. Ara crec que s'ha d'obrir a preguntes, no? Sobre qualsevol dels projectes. Ja sé que és molta informació variada en poca estona, però la intenció és que fos això, més o menys divulgatiu, donar una imatge dels projectes que estem fent en microenergia al grup.
Y Lliber, Carlos, abrís vosotros también la cámara si podéis.
Podem.
Per pregunta a la Francesca, suposo, si tens micròfon, activar-lo.
Espera, al chat.
Sí.
Hola, soc el Lluís. Una pregunta.
Hola.
Carlos, aquestes... Hem de fer les preguntes en anglès, també?
És lliure.
Jo he mirat la llista de persones presents. L'única persona que crec que no parla català o castellà és l'Arani. Però n'hi ha una.
Well, in any case, in your presentation you have shown a few plot graphs regarding current, for instance, and playing with the materials and the loadings and so on and so forth. And those curves, with time, the current was decreasing quite a bit. What's behind this? Is the material is not stable, or this is some state of things that need to stabilize? And
all the reported papers, they behave in the same way. It is not fully understood. I had here, well, actually, no, I don't.
And which was the scale of time? It were tens of minutes, or?
So in here, it reaches more or less stability in a couple of minutes. But in this one, or this one, it took up to 50 minutes to reach some. It didn't even reach full planarity. But yeah, I mean, it is reported. I don't really understand the mechanism. This is short circuit, and I think it subtract a large amount of electrons in a relatively fast time, and reach this point, when it reaches the plateau. I think it because the current is just generated, or it's let's say driven by the kinetics inside the device. So all the new protons that detach are the equivalent to the current that is being generated, while on the all this transitory state, there is an accumulation of protons, which was not still steady. I don't know if I'm explaining well, because I don't understand it very well.
Thank you.
But that's in literature, everybody is reporting this behavior. VOC, however, for the voltage, the behavior is different.
We are not seeing your presentation. If you are pointing to a graph, we are not seeing it.
I was trying to, sorry. Let me see. Compartir. Okay. Can you see this now?
Yes.
Okay. So yeah, for the VOC, you might not see it here. I don't have here. No, I don't. The behavior is different, and that it's kind of explained in the literature. So we have this state, when the steady state, but when you close the circuit, more protons will go towards the cathode, and then the VOC has this shape of increasing the VOC until reaching a new steady state, which is when the circuits close. It's not close, and that's something we were discussing with Marc. When you begin measuring a VOC, well, what I read in some papers, they justified like they can see through the circuit, they can see the anode part. So there will be more protons traveling toward the cathode when you begin measuring. Not applying a load resistance, but just measuring. It's not clear. There are just new Nature materials papers stating that it is not understood, and there is a little confusion from people saying one thing and other people saying the different. So that's, I believe, is an opportunity also to further dig in this mechanism and try to understand it better.
Mm-hmm. And when you say that this was in the field on the wall of green, is because of the materials that are used?
Well, I mean, I would say the materials, of course, they need to be green for this kind of technologies. Otherwise, in my opinion, doesn't make sense. But I think it's more because of the source of energy is from air. I mean, okay. It's from the air that we breathe, and also because my goal is to have this technology working at humidities of around 30% or even under 30%, meaning that they can operate in any place in the planet, even in the deserts. The relative humidity at deserts, it's 20% or over. So it's ubiquitous. We have these source of energy is everywhere at every time in the planet.
Thank you, Carlos.
Francesca pregunta aquí amb les paraules, si ja està. Lluís, tens la paraula, Francesca, si pots...
Em sentiu?
Sí.
Vale, és que no, l'última vegada va ser impossible per mi que em sentíssiu. Vale. No, a la Llibertat li preguntaré directament perquè la tinc aquí habitualment. Una cosa, Marc, la teva presentació, quines dimensions té el dispositiu? Perquè a les imatges em sembla que era la pàgina 7 o... Bé, és igual.
Sí,
Quan una cosa és el dispositiu, l'altra és on poses la placa i després acabes posant una mena de refrigerador, no?
Sí, espera, no sé per què no
Llavors,
puc...
quines dimensions té tot plegat? Que això ho he perdut.
Sí, el xip sencer, aquí tens l'imatge més o menys.
Sí,
El xip
exacte.
d'aquesta
Això és el
plataforma
xip.
fa 1,5 per 1,5, la part on hi ha membranes i parts
Sí,
funcionals fa
sí.
1 per 1, i cada una de les membranes són diferents dimensions perquè és precisament el que volem testejar, no? Les variabilitats que tenim.
Bueno, això és perquè esteu avaluant diferents
Exacte, i és al
aspectes,
voltant
no?
d'un mil·límetre quadrat cada una.
Clar, però després acabes tenint quines dimensions? Això, aquest sistema de baix, la placa de baix.
Sí, la placa, això és un esquema perquè s'entengui, el xip és 1,5 per 1,5, sí que tenim plaques petites, però no són aquestes, al final el que et puc ensenyar és això. Això és una
Exacte,
placa
aquí,
més gran.
aquesta, sí.
Sí, aquesta deu
D'això
fer
de...
10 per 10 centímetres. No, 10 per 10 no, 5 per 5, perdó.
Vale.
Això és el xip de 1,5 per 1,5, és una placa que fem servir aquesta perquè tenim un setup ja al laboratori preparat per
Sí, bé,
per caracteritzar.
No, és que aquí aquestes imatges no sabia de quines dimensions estàvem parlant. Llavors, una pregunta. Els materials que feu servir, per exemple, en aquesta imatge en B perfecta, esteu fent servir com a metall titani wolframi?
Sí, el titani és per millorar l'adherència.
Bueno, això és, o sigui, el titani per vosaltres és l'adherència, llavors hi poseu el
Tungstè.
wolframi. Llavors, aquesta és una combinació que és l'òptima pels vostres objectius o...
El tungstè ja el van fer servir en els nanofils de silici perquè havien de sobreviure al procés de creixement dels nanofils en el seu moment, que era un procés que es feia a 500, 600, 700 graus de temperatura.
Sí.
I aquest material és el que van validar en el seu moment que ens funcionava. Vale? I actualment aquests també, perquè aquest, a més, totes les perovskites, com el titanat d'estronci de fet funcionen o han de competir amb aplicacions que sempre són a altes temperatures, perquè tenen millor rendiment que el bismut tel·luri, que és el que domina el mercat a temperatura ambient.
Vale. No, és que aquí he vist una oportunitat que potser fora interessant, per això ja en parlarem, d'afegir més coses i potser la mateixa estructura posar-hi alguna cosa addicional, no? Per això no sabia si era ocasional l'ús del tungstè o realment és l'oportú. I llavors has comentat que aquí esteu afegint l'opció de les perovskites. Quin és l'interès? Perquè les perovskites a mi em dóna la sensació que són materials que s'ha publicat molt, però tenen alguns inconvenients greus de funcionament a llarg per aplicacions. Llavors, quin és l'interès d'estudiar les perovskites per a aquestes aplicacions?
L'interès per part nostra és, evidentment, perquè no està publicat i creiem que té potencial si es parla de nanoestructurar, o sigui, fer capes primes d'aquest material, perquè llavors tèrmicament es comporten millor, tenen millor CIVEC i només ens falta dopar-les, o sigui, que tinguin millor conductivitat elèctrica. I per això hi ha tots aquests els high entropy oxides que tenen diferents... pots millorar les propietats elèctriques del material i millorar el ZT. El ZT no està tan lluny d'aplicacions comercials. De fet, a veure si tenia... Aquí, veus? Aquí hi havia un altre resum que hi havia un llistat, no? Aquests, per exemple,
Sí,
són...
no, però això no, ja entenc que teòricament té unes bones prestacions o uns valors dels paràmetres idoni, però potser tinc una informació incorrecta, però gent que ha treballat o treballa amb aquests materials diuen que es degraden només de mirar-los. Llavors, aquesta és la pregunta, no?
Doncs no és el cas, perquè de fet aquesta mostra que tens aquí davant ha estat sotmesa durant bastants dies i setmanes, et diria, a diferents mesures i està estable i a diferents temperatures. Veus, a 175, 200 graus de temperatura no hi ha hagut degradació ni s'ha format cap. Això no ha deixat de ser funcional, la capa. Això, en tot cas, és la part que desenvolupa IREC, que IREC ja són, evidentment, utilitzen tots aquests materials com electrodes o electrolits de les seves piles de combustible, i una de les aplicacions que vam veure després de les moltes col·laboracions que tenim va ser aplicar-ho a termoelèctrics, perquè no és un camp desconegut i, a més, té potencial.
Sí, no, veiem, efectivament. Jo he entès que els del material són els de l'IREC. El que jo estava parlant és de gent que ha treballat molt amb perovskites per aplicacions a cel·les solars. Vull dir que és i reconeixen això, d'acord? Tot i que hi hagi moltes publicacions, etc. No? Era per això. O sigui, de fet, és aprofitar, diríem, la vinentesa de l'expertise no? Entenc que és això i avaluar què passa. Està bé. Tot molt interessant, la veritat. Us felicito per totes les activitats. Digues.
Perdoneu que entri una mica a la discussió, però aquesta mateixa pregunta els hi vaig fer els de l'IREC i la resposta va ser en la línia de que ells no pensaven ells no pensaven implementar capes ultraprimes en aquest tipus de dispositiu, precisament pel que comentes, no? Per la degradació de moltes de les propietats en capa prima. Però ells pensaven, sempre comenten de 100 a 200 nanos de gruix, en els que els efectes de volum guanyen molt a la superfície. El problema de les manganites és normalment de tensió i normalment a les superfícies. A partir de 100 nanos la cosa sembla ser que va una mica millor. Però sí que tens raó en aquesta cosa, jo els hi vaig comentar. I sempre han parlat de capes primes, però no són capes primes com les que habitualment se'n parla, de menys de 50 nanos. Se'n van a més amunt de 100.
Ara veig el punt, clar. L'altra cosa que jo també em qüestiono sovint és l'escalabilitat d'una operació feta en PLD. Jo això no sé si us ho heu plantejat. Ja sé que estem parlant en termes recerca, però això ho veig un punt feble. Bé, res, només era aprendre una mica sobre això que esteu fent. I ara tinc una pregunta absolutament de pura curiositat, que és el Carlos, que ens ha presentat un projecte amb un nom d'un grup musical que jo diria que el 90%, i em sembla que sóc generosa, dels assistents no saben ni qui són. Llavors, em pregunto d'on surt on està el punt de posar aquest nom a aquesta activitat.
Bueno, gràcies per la teva pregunta. No sé, estaria bé. Jo diria que el percentatge és força més elevat. Jo crec que és un grup força conegut. No sé, potser m'equivoco.
No, jo no dic el món, estic parlant...
No, sí. Bueno, clar, no conec tothom aquí, però vaja, jo diria que és força conegut. I la raó no és només pel projecte aquest, de generació d'electricitat, sinó que també és perquè volia fer una cosa més conjunta per water harvesting. Els mateixos materials serveixen per harvesting d'aigua atmosfèrica i volia fer una cosa, i per això també el càntir, volia fer una cosa més tipus un dispositiu que pot agafar aigua de l'ambient i, a més de produir aigua per beure, pot generar electricitat. Llavors sí que és una cosa més de l'aigua com un tema dogmàtic, no? La creença de que l'aigua que tenim aquí té futur, no?
Bueno, aquí al desert, perquè això també donaria aigua al desert, vaja.
Correcte.
Vale, gràcies,
Doncs ara jo reconec que no el conec i que hauré de seguir Google.
De veritat?
De veritat.
Segur que sentiu cançons, els coneixeu tots.
Jo també us dic una cosa. A mi em va fer molta gràcia veure això, aquest nom, no? Perquè va ser el primer, que jo primer tenia discos LP, vinils, no? En diuen ara, abans se'n deien discos. Llavors, jo tenia vinils i llavors una vegada vaig tenir un aparell de reproductor de cassets I el primer casset que vaig comprar, bueno, que vaig comprar no, que em devien regalar, que era molt joveneta, va ser un casset d'aquest grup. I per això em va fer molta gràcia, que tinc el primer casset comprat va ser d'aquest grup. I estic parlant de fa uns quants anys, Llavors, per això em dóna a mi la sensació que tan conegut el grup, no sé. Potser tens raó, Marc, que segurament les cançons sí que són...
Exacte. El nom no, però les cançons segur. Bueno,
Si
però així
queréis
tothom
hacemos
tindrà...
una encuesta rápida.
Pues hazla, sí.
Y que vote la gente.
Jo voto per 60 que el coneixen.
Sí que es
60-40, sí.
Jo vaig cap a 70.
70-30.
Jo no veig l'enquesta.
A ver,
Està
ya he
fabricant.
creado, entonces
Ah.
convertir.
Ara veurem.
Sabela,
Instant.
Sabela, una pregunta. Pels que no
Sí.
els coneixen, podríem ficar potser la cançó aquella de Have You Ever Seen the Rain?
Sí,
I llavors jo crec que hi ha molta gent, els hi sonarà la cançó, però no l'hauran associat amb aquest grup que té aquest nom tan divertit i que ens pot portar tantes alegries a l'hora de recuperar energia a partir de la humitat.
claro. Ahora, ¿no? ¿La veis?
Sí.
Sí, sí.
Jo ja he votat, però ja sabem el
També he
vot.
votat.
Jo com a cojos no em deixa, no? Veig, o sí?
Sí, no, a mí tampoco me deja, pero...
Mira, 60-40. He guanyat.
60-40.
Ja està.
No, 50.
On té?
Bueno, però
Ho
falten
No ho veig.
ho
No,
veieu
no.
vosaltres només els coordinadors.
M'ha fet un pop-up, a mi m'ha sortit a davant.
Ahora esperamos. Han votado ya 12, 11, 23. ¿Cuántas personas quedamos? 28. Bueno, la cerramos.
Veig que el Perpi ha compartit la cançó, no?
Sí.
50-50.
Però vaja, en tenen moltes de conegudes, no només una.
Sí,
no,
però
la
potser aquesta és la
desconocen.
més coneguda, no dic la millor, però és la més coneguda, crec, Aquí
Sí,
també
sí.
podríem obrir una altra votació, vale? Però, bueno, és
Bueno,
per
ara-
posar un exemple.
M'ha quedat
Ara
un
s'ha-
50-50, això,
Ara se sentirà pels passadissos del CNM. Carlos.
Escolta, Marc, una pregunta. Tornant a la teva presentació del siliciur de crom, que has presentat resultats i deies que es vol construir a partir de silici, però també de polisilici, no?
Sí.
Llavors, quan es fa a partir del polisilici, no sé si és per un tema de flexibilitat dels materials, però clar, polisilici té fronteres de gra. El material resultant, penseu que tindrà propietats diferents que el que es creix sobre silici i que serà a favor o en contra de les propietats termoelèctriques? O sigui,
Pel que sabem serà doble, Vull dir, serà un intermig, no? O sigui, elèctricament serà pitjor, però tèrmicament serà millor, perquè el poli ajuda, ja té més fronteres de gra, doncs evita uns quants fonons pel camí, amb la qual no sé si serà millor o pitjor, però això ens ajuda en el procés de fabricació, vale? Perquè no sempre hem d'utilitzar olees soy, que integrar les olees soy amb aquella plataforma que tenim encara ho hem d'estudiar, perquè sí que ho tenim pensat pel dispositiu final, no? Adaptar les sois al dispositius tipus Minauto, que tenen més densitat d'integració, però la plataforma de zero és més complicat integrar-hi una soy. I aquesta era la raó, Vull dir, avaluar si podem fabricar de la mateixa manera el siliciur de crom en substrats polisilici, que ens ajudarà a avaluar les seves propietats. Però no sé si serà millor o pitjor globalment, sí que sabem que una qualitat pujarà, però l'altra empitjorarà.
gràcies.
Molt bé.
Vale. Sí, Marc, cierra tú. Sí.
No, preguntava si hi havia més preguntes i si no, que tothom que escolti les cançons i es posi al dia.
Sí, pues cerramos entonces, que ya es la 1, y la segunda parte de estos workshops de energía con proyectos será el 14 de marzo, así que apuntaos la fecha. Y las charlas de los viernes igualmente vuelvo a ver el 21 de febrero otra, así que nos volveremos a ver ahí. Gracias a todo el mundo.
Molt bé, merci Isabela. Gràcies.
Gràcies.
Adéu.